Simon, nuclear decay and the binding energy. The first 18 question we did in the session. So question 19 today. In this question, the first example of artificially produced radioactive isotope was in 1934. So in 1934, because radioactive isotopes can be natural or it can be artificial or a man-made. So artificial radioactive element was formed in 1934. We have to complete this equation to represent, like, they bombard an aluminum with an alpha particle to produce an unstable isotope of phosphorus. You have to complete a nuclear equation to represent this process and identify the particle X. So first, alpha particle, the nucleon number is 4 and the proton number is 2. So we write 4 here and 2. The sum should be same, like 27 plus 4, 31 on the right hand side. So it should be 31. So 30 is there. So means this should be 1 to make 31. Proton number should also be same. So this one is 13 plus 2 makes 15. So this is 15 means this should be 0. So which particle is having a nucleon number 1 but there is no charge on it? So what is this particle? This particle is actually a neutron. So this is neutron is produced in this. The next part, the alpha particles had a kinetic energy of 5.3 mega electron volt. Calculate the total kinetic energy of a reaction product. So we assume like alpha particle is bombarded on the aluminum, like the bombarded aluminum with alpha particle to produce. So we consider aluminum does not have kinetic energy. In the beginning, its kinetic energy is 0. What we work out, like the total mass plus kinetic energy, because we will work out the mass defect and that mass defect has basically converted into. So we need to calculate the total energy of the product, kinetic energy of the product. We want to calculate how much kinetic energy is there for this whole product. So first, we'll find the mass defect, like how much mass difference is there. So how to work out the mass defect? We have the mass of alpha particle here. We have the mass of aluminum. So this will be the reactant. And the product is the mass of a proton is there and mass of neutron, because this is a neutron, not a proton, and the phosphorus. So by just substituting the values, so working out the mass defect, aluminum is 26.9. You have to use all the numbers here because the mass defect will be small. Plus alpha particle is 4.001506. That is the mass of reactant minus the mass of a product. The product is phosphorus 29.97831 plus the neutron is produced. So the mass of a neutron is 1.0086665. This will give us the mass of a reactant minus the product will give us the mass defect, like how much difference in the mass is there. But this answer will be in atomic mass unit or AMU. So how much is the mass defect? The mass defect is, it will be negative because it's 29 here and this 26. When you sum, it will be negative. So it will be minus 0.003929 atomic mass unit, AMU. But we have to convert the AMU into kilogram. 1 AMU, 1 atomic mass unit is equals to 1.66 into 10 to the power minus 27 kg. So we multiply by this factor by 1.6 into 10 to the power minus 27. So this will give us how much. Basically, the mass has the difference when it means the mass has increased. But how the mass increased? Like some of the kinetic energy is actually used to convert into mass here. That's why the alpha particle was moving, will have a kinetic energy. So this was 6.52 into 10 to the power minus 30 kg. Now we work out how much energy is needed, extra energy. So E is equals to mc square. So delta m and c square. So this was minus 6.52 into 10 to the power minus 30 times the speed of light square. So 3 into 10 to the power 8 and then square. So this is the energy which we need, extra energy. We need 5.87 into 10 to the power minus 13 joule. If we convert into electron, because the energy which we, extra energy which we, what we have to work out, we have to work out how much kinetic energy for the product. So this is the energy, total energy which we need, which include like energy need, extra energy which we need. And from where we get this extra energy, we'll get this extra energy from the kinetic energy of alpha particle, and remaining of that energy is used as a kinetic energy of the product. So 5.87 into 10 to the power minus 13, we convert this energy into electron volt. How to convert into electron volt? 1 electron volt is equals to 1.6 exponent minus 19. So we divide by 1.6 exponent minus 19 to convert this joule into electron volt. And then we convert into mega electron volt. So that will give us minus 3.67 mega electron volt. Means this is the energy we need to produce this particle and move them. Not only to produce, but to move them as well. Sorry, this is the energy we need to produce the particle because we are finding a mass defect, not to move them. So the total energy of the alpha particle which we used for this reaction was 5.3. So this is the energy of alpha particle we use. Out of this, 3.67 has used to produce the particle, and remaining of that will be used as a kinetic energy. So the alpha particle energy, because the idea is that this is the amount of energy we need to produce these particles, like because the mass has to be increased. So that's why the mass defect was negative. If mass defect is negative, it means the mass has to be increased. And to increase this mass, we use a kinetic energy. Some of the kinetic energy of alpha particle is used to increase the mass, which is equivalent to minus 3.67 mega electron volt. And remaining of that energy is used to move the fragments or the product. So 5.3 minus 3.67, which is equals to 1.6 mega electron volt. So 1.6 mega electron volt is the kinetic energy of the fragments. Is it clear, this part? In the next part, part B, the phosphorus 30 is a positron emitter. Positron emitter means like it opposite of electron, antiparticle of electron. What is meant by the term positron, and suggests why positron emission is unlikely to occur for a nucleus with an excess of a neutron. Basically, there are two beta emissions. One is the negative beta decay, which is called electron, in which the neutron breaks into proton and electron. This is called a negative beta. And there is another in which the proton breaks into neutron and positron, which is also known as a positive beta decay. So what is meant by a positron? What is a positron? Positron is actually an antiparticle of electron, or positron is anti-electron. It has like opposite spin, opposite charge. And what else? Why, like a why a nucleus which is having excess of neutron is less likely to emit positron? Because positrons are produced by protons, not by neutrons. So if excess of neutrons are there, then negative beta decay or electron emission is likely to occur. So positron has the same mass, but same mass as electron, but different charge. Like opposite charge, not different charge, opposite charge. And because for positive positron emission, we need neutron. Otherwise, if more protons are there, then it will emit out. If for positron emission, we need more proton. If it is like a nucleus is having more neutrons, so it's less likely to emit out positron. Otherwise, the charge won't be conserved. Then phosphorus 30 has a half-life of 150. At particular instant, it contained 2.2 exponent 16 atom. Calculate the activity. So activity is basically like how many nucleus decay in 1 second. That is called activity. And activity is also given by a formula A is equals to n lambda, where n is the number of the nucleus present and lambda is a decay constant. We have the number of the nucleus present, which is 2.2 into 10 to the power 16. The decay constant, we can work out the decay constant from half-life because decay constant is 0.693 over half-life. So we can write 0.693 over half-life, which is 150. So because the time, like activity is in the decay time, half-life was in second. So decay constant, the activity will be in like how many disintegrate per second or number per second, which is, and the unit of activity is becquerel, BQ. So when we simplify this, the decay constant times the number of the nucleus present, so it will be 1 exponent 14 becquerel. Becquerel here refers to how many atoms disintegrate in 1 second. Then determine the activity of a sample 15 minutes later. So how we work out, we'll use a formula A is equals to A naught e raised to the power minus lambda t. So new activity is A, original activity is A naught, which we work out like 1 into 10 to the power minus 14. E raised to the power minus lambda and t. T is the time we want to find after 15 minutes, but because the decay constant all were in seconds, so that's why you have to convert this time also in second. So 15 multiplied by 60, you will convert into second. So A equals A naught. The original activity is 1 into 10 to the power minus 14. E raised to the power minus lambda we work out, which was 0.693 over 150, the half-life. So lambda was 4.6 into 10 to the power minus 3 for this, and the time should be in second. So it will be 15 minutes, you multiply by 60, so it will be in second. When you simplify, the original activity, this answer, it was not minus, it was plus 40. So one exponent 14 was there, becquerel. When you simplify this, this will give you the new activity, which is 1.56 into 10 to the power 12 becquerel. So the activity of a sample decreases with time. In the beginning, we have maximum activity, where it's like more radioactive atoms. But with the passage of the time, the number of the radioactive atoms start to decrease.